Every way to solve quadratic equations. Factoring. This is the commonest method for solving quadratic equations. Let's see how it works. X squared plus 11x plus 28 equals 0. To solve this, we need two numbers whose product is 28, the last term in the equation, and whose sum is 11, the coefficient of x. To get these two numbers, we have to guess and check. We will start with the product and then check the sum. 1 times 28 is 28, but the sum of 1 and 28 is an 11. 2 times 14 is 28, but the sum of 2 and 14 is an 11. 4 times 7 is 28, and their sum is indeed 11. So those are the two numbers we're looking for. Now, what we are going to do with those two numbers is write 11 in terms of 4 and 7. So 11x now becomes 4x plus 7x. Now, our equation is x squared plus 4x plus 7x plus 28 is equal to 0. We can group the first two terms and then group the last two terms. We can factor x out of the x squared plus 4x, and we get x times x plus 4. And we can factor 7 out of 7x plus 28, and then we get 7 times x plus 4. Next, factor out x plus 4, and we get x plus 4 times x plus 7 equals 0. Now, using the zero product property, which says that if a times b equals 0, then a equals 0 or b equals 0. We can equate each term in our product to 0, which is x plus 4 is equal to 0 or x plus 7 is equal to 0. And finally, x equals negative 4 or x equals negative 7. It is important to note that not all quadratics can be solved by factoring because simple factors may not exist. So, when does this work? For the equation ax squared plus bx plus c equals 0, we can solve by factoring when the discriminant b squared minus 4ac is equal to a perfect square. If b squared minus 4ac equals a perfect square, then simple factors exist. If b squared minus 4ac equals 0, then the quadratic may or may not be solvable by factorization. It will be a repeated root, but that can sometimes be irrational. Let us use some examples to clarify this. X squared minus 2x minus 1 is equal to 0. Let's calculate the discriminant. B squared minus 4ac equals minus 2 squared, minus 4 times 1, times negative 1, which equals 4 plus 4, which equals 8. 8 is not a perfect square, so this quadratic equation cannot be solved by simple factoring. Let's use another example. X squared plus 8x plus 15 is equal to 0. B squared minus 4ac equals 8 squared, minus 4 times 1, times 15, which equals 64 minus 60, which equals 4. 4 is a perfect square, so this quadratic equation can be solved by simple factoring. Po-Shen Loh. Let us use an example. X squared plus 10x plus 24 equals 0. As usual, we want two numbers whose product is 24 and whose sum is 10. But we are going to do this without guessing and checking, but by calculating. First, we are going to divide b, which is the coefficient of x, by 2. After that, the numbers we are looking for are 5 plus u and 5 minus u. Since the product of the two numbers should equal 24, then 5 plus u times 5 minus u should equal 24. You may notice that the left-hand side is a difference of two squares. So that becomes 25 minus u squared is equal to 24. Solving this gives us u squared equals 1, which means u equals plus or minus 1. Choosing either won't change the solution. We are going to use plus 1. Since u equals 1, our two numbers are 5 plus 1, which equals 6, and 5 minus 1, which equals 4. We just found the two numbers whose product is 24 and whose sum is 10 without guessing and checking. Now everything is just like we did for the factoring method. X plus 6 times x plus 4 equals 0. And from the zero product property, we get either x plus 6 equals 0 or x plus 4 equals 0. Finally, we get either x equals negative 6 or x equals negative 4. Now, let's try to understand how this works. This was our equation, x squared plus 10x plus 24 equals 0. Our target product was 24, and our target sum was 10. This time, let us start by guessing the sums. Two numbers with a sum of 10. 1 and 9 add to 10, but their product is not 24. 2 and 8 add to 10, but their product is not 24. 3 and 7 add to 10, but their product is not 24. 4 and 6 add to 10, and their product is indeed 24. Now let us look closely at our number pairings. 1 is 5 minus 4, and 9 is 5 plus 4. 2 is 5 minus 3, and 8 is 5 plus 3. 3 is 5 minus 2, and 7 is 5 plus 2. 4 is 5 minus 1, and 6 is 5 plus 1. What exactly is going on here? Any two numbers are always the same distance from their average, and on either side of their average. Since the sum is 10, they all have an average of 5. An equal distance on either side of 5 can be represented by 5 plus u and 5 minus u. So, in general, we can write that sum divided by 2 plus u times sum divided by 2 minus u equals the product. No need for guessing and checking. This method was rediscovered by American mathematician called Po-Shen Loh, but it was originally discovered by the ancient Babylonians and the ancient Greeks independently. Completing the square. Let's use the same example we used for factoring. X squared plus 11x plus 28 is equal to 0. The first thing is to subtract c. We get x squared plus 11x equals minus 28. Next, we add half of b all squared, that is b squared over 4, to both sides of the equation. That gives us x squared plus 11x plus 121 over 4 equals negative 28 plus 121 over 4. After completing this step, the left-hand side of the equation becomes a perfect square of the form x plus b over 2 all squared. So our equation is now x plus 11 over 2 all squared equals 9 over 4. The right-hand side computes to 9 over 4. Square root of both sides. We get x plus 11 over 2 equals plus or minus the square root of 9 over 4. We get x plus 11 over 2 equals plus or minus 3 over 2. Therefore, x equals minus 11 over 2, plus or minus 3 over 2. Finally, x equals negative 4 or negative 7, as expected. Now, let us try to understand what completing the square really means. Let us consider a perfect square quadratic of the form x plus p squared is equal to x squared plus 2px plus p squared. An example is x plus 5 squared equals x squared plus 10x plus 25. Let's say we want to solve x squared plus 6x plus 8 is equal to 0. We need to find a perfect square closest to x squared plus 6x plus 8, and that is x squared plus 6x plus 9, which is x plus 3 squared. Comparing them, they differ by 1. X squared plus 6x plus 8 is equal to x squared plus 6x plus 9 minus 1, which is x plus 3 squared minus 1. Solving that, we get x plus 3 squared equals 1. X plus 3 equals plus or minus 1. Finally, it is x equals minus 2 or x equals minus 4. So it is all about transforming our quadratic to look like a perfect square. Now let us generalize what we mean by transforming our quadratic to look like a perfect square. Consider the expression x squared plus bx plus c. Let's find the closest perfect square to this. In this case, this is x squared plus bx plus 1 over 4b squared. Now, how do we transform our expression to the perfect square expression? Simple. Subtract c, and then add 1 over 4b squared. This is why, when we were completing the square in the original example, we first subtracted c and then added 1/4 b squared. When completing the square, always make sure the coefficient of x squared is 1. Let us use geometry to understand completing the square. We have x squared, which as the name suggests is a square with dimensions x, plus bx. Bx is a rectangle with dimensions b and x and area bx. Finally, plus c. C could be any shape, but let us use a rectangle here, and it has area c. First step is to subtract c, so we subtract c and remove the c rectangle. Next step is that we half bx. Now we attach half bx to the sides of x square. So we create a new square, in quotes, with dimensions x plus b over 2. But this new shape is missing a piece before it actually becomes a complete square. We need to add the missing piece to complete the square. This is why this process is called completing the square. If you observe carefully, the dimensions of the missing square is b over 2. Let us now introduce the missing square to complete our square. The area of the missing square is b over 2 squared. Now this is why, after subtracting c, we add b over 2 squared, or 1 over 4b squared to complete the square. The quadratic formula. Let us use our previous example once again. X squared plus 11x plus 28 equals 0. The formula for the roots is minus b plus or minus the square root of b squared minus 4ac divided by 2a. To find the roots, we solve minus 11 plus or minus the square root of 11 squared minus 4 times 1 times 28 divided by 2 times 1. And now we have minus 11 plus or minus the square root of 121 minus 112 divided by 2. And now we have minus 11 plus or minus the square root of 9 divided by 2. And that equals minus 11 plus or minus 3 divided by 2. Finally, we have x equals minus 4 or x equals minus 7. Now, how do we derive the quadratic formula? Let's consider a quadratic in the standard form ax squared plus bx plus c equals 0. What we are going to do is complete the square. First thing is to divide through by a. Now we have x squared plus b over ax plus c over a. Next, subtract c over a from both sides. So, we have x squared plus b over a equals minus c over a. Next, add b over 2a squared to both sides. That is, add half the coefficient of x squared to both sides. So we have x squared plus b over ax plus b over 2a squared equals minus c over a plus b over 2a squared. Then we have x squared plus b over ax plus b over 2a squared equals b squared over 4a squared minus c over a. The left-hand side is a square of the form x plus b over 2a, all squared. Next, the left-hand side becomes x plus b over 2a, all squared, equals b squared minus 4ac divided by 4a squared. We had x plus b over 2a, all squared, equals b squared minus 4ac divided by 4a squared. Now, find the square root of both sides. X plus b over 2a equals plus or minus the square root of b squared minus 4ac divided by 4a squared. Since the square root of 4a squared is 2a, x plus b over 2a equals plus or minus the square root of b squared minus 4ac divided by 2a. Subtract b over 2a from both sides. X equals b over 2a plus or minus the square root of b squared minus 4ac divided by 2a. Since 2a is a common denominator, we have minus b plus or minus the square root of b squared minus 4ac divided by 2a. This is the quadratic formula. This formula fails when a equals 0. That is when we have a linear equation. This is because there is an a in the denominator, which causes division by 0. This is important if you have a model where a is varying. Muller's method. This is similar to the quadratic equation. Let us use the same equation. X squared plus 11x plus 28 is equal to 0. The roots of the equation are given by 2c divided by minus b plus or minus the square root of b squared minus 4ac. So let's try it. X is equal to 2 times 28 divided by minus 11 plus or minus the square root of 11 squared minus 4 times 1 times 28. Next, x is equal to 56 divided by minus 11 plus or minus the square root of 121 squared minus 112. Next, x is equal to 56 divided by minus 11 plus or minus the square root of 9, which is equal to 56 divided by minus 11 plus or minus 3, which means x equals 56 over negative 14, or x equals 56 over negative 8, which means x equals minus 4 or x equals minus 7 as expected. Let us look at one way of deriving this formula. Let's consider a quadratic in the standard form ax squared plus bx plus c equals 0. The first thing is to divide through by x squared. That is a plus b over x plus c over x squared is equal to 0. That is a plus b times 1 over x plus c times 1 over x squared is equal to 0. Rearrange this to get c times 1 over x squared plus b times 1 over x plus a is equal to 0. Now, let us write the quadratic formula for the original equation. Now our modified equation is in terms of 1 over x. A is now c, b remains b, c is now a. Swapping a and c, we can write the quadratic formula for 1 over x. Inverting this so we get x on the left-hand side, we get the new quadratic formula known as Muller's method. You can also derive Muller's method by rationalizing the numerator of the original quadratic formula. You can test whether this is equal to the original quadratic formula by cross-multiplying them. This formula fails when c is equal to 0. AC method. This is factoring when a is not equal to 1. Let's use the equation 12x squared plus 17x plus 6 is equal to 0. We first multiply a and c, 12 and 6, and get 72. The sum remains b, which is 17. We need two numbers whose product is 72 and whose sum is 17. 1 times 72 is 72, but their sum isn't 17. 2 times 36 is 72, but their sum isn't 17. 3 times 24 is 72, but their sum isn't 17. 4 times 18 is 72, but their sum isn't 17. 6 times 12 is 72, but their sum isn't 17. 8 times 9 is 72, and their sum is indeed 17, so that is our number pair. As usual, we write 17 in terms of 8 and 9. Factor 4x out of the first two terms and factor 3 out of the last two terms, and now our equation looks like this. Next, factor out 3x plus 2, and now our equation looks like this. Using the zero product property, which says that when a times b equals 0, then either a equals 0 or b equals 0. So for x plus 3 equals 0 or 3x plus 2 equals 0. Finally, x equals negative 3 over 4 or x equals negative 2 over 3. Substitution. Just like the AC method, this is also used when a is not equal to 1. In this process, we substitute x with a different variable, solve, and convert back to x. How do we do it? First, multiply 12 and 6, that is a times c. Replace c with the result, that is 72, and then replace a with 1. Our new equation is p squared plus 17p plus 72 equals 0. Solve this equation by factoring. Find two numbers whose product is 72 and whose sum is 17. Go through the process of solving by factoring and solve for p. You get p equals negative 8 or p equals negative 9. Now how do we convert from p back to x? We simply divide through by a from the original equation. A was 12 in the original equation. So, we have x equals minus 9 over 12 or x equals minus 8 over 12. Finally, reduce the fractions to the lowest terms, and we have x equals minus 3 over 4 or x equals minus 2 over 3. Now let's see why this works. So this was our original equation. This was our modified equation. This is the quadratic formula for our original equation. Comparing the two equations, we can see that a becomes 1. B remains the same as it was. C changed from 6 to 12 times 6, which is AC. Rewriting our quadratic formula with these changes. So we replace a with 1, and then we replace c with AC, and b remains the same. Simplifying further, we get an equation very similar to the original quadratic formula, but with one change, the a in the denominator. To go from p to x, that is, to go from the new solution to the original solution, all we have to do is divide through by a. That is why we divided through by a after solving for p. Continuous fractions. Consider a quadratic of the form x squared plus bx plus c equals 0. Its solution can be found using continuous fractions as follows. X equals minus b minus c divided by 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 minus b, and so on and so forth. You cannot use this formula when b equals 0. This is because the continuous fraction diverges when b equals 0. You can still solve using continuous fractions, but not this formula. You have to use a workaround. This formula also diverges when the discriminant is negative. That is when the quadratic has complex roots. It converges when the discriminant is equal to 0. The quadratic has repeated roots, and it converges to the repeated root. It converges when the discriminant is positive, and it converges to the root with the larger magnitude. Doesn't matter if it is positive or negative. Let us solve an example using continuous fractions. Using the example, x squared plus 11x plus 28 is equal to 0. Substitute b and c into the formula, and this is what it looks like. Now let us solve it in steps. For the first step, we go down to a depth of 1, and we have x equals minus 8.454545. Next, we go down to a depth of 2, and we have x equals minus 7.68817. Next, we have x equals minus 7.35804. Then x equals minus 7.19464. At a depth of 5, we get x equals minus 7.10821. The values are slowly converging to a value of negative 7. Negative 7 is indeed a solution to the quadratic equation, and it is the one with the larger magnitude. To find the other solution, you can use Vieta's rule, which says the product of the roots is c over a, which is 28. 28 divided by negative 7 is negative 4. The rate of convergence depends on the ratio of the absolute values of the roots. We will use the magnitude of the larger root divided by the magnitude of the smaller root. The bigger this ratio, the faster the continuous fraction converges. Our solutions were negative 7 and negative 4. The two solutions are close in magnitude, and that is why our continuous fraction was taking forever to converge. Trigonometric solution. Let us say the equation is of the form ax squared plus bx plus or minus c is equal to 0. The roots of the equation will be x equals the square root of c over a tan theta. Substitute this equation of x into the equation above, and then multiply through by cos squared theta over c. This is what our quadratic equation now looks like after those two steps. You can derive two equations from this, one for tan 2 theta and one for sine 2 theta. The subscripts n and p represent positive and negative, in reference to whether the sign before c is plus or minus. These two equations are solved for theta, and then the value for theta is used in the equation for x to find the roots. Let us use the example x squared plus 11x plus 28 equals 0. X is equal to the square root of 28 over 1 tan theta, which simplifies to x is equal to 2 root 7 tan theta. Since the sign before c is positive, we are going to use sine 2 theta sub p, which is equal to 2 root 28 over 7. There are two solutions. Theta 1 is minus 36.08668. The second solution, theta 2, is 127.08668. Now we have to put both values of theta into the x equation. The first solution is 2 root 7 tan minus 36.08668, which results in minus 3.9999, approximately the minus 4 we expect. The second solution is 2 root 7 tan theta 2, which is 2 root 7 tan 127.08668, which results in minus 7, exactly as we expect. Vieta's rule. Let us use the example 2x squared minus 7x plus 3 equals 0. Vieta's rule says that the product of the roots is c over a, and the sum of the roots is minus b over a. In this case, the product of the roots is 3 over 2, and the sum of the roots is 7 over 2. By guessing and checking, we get one root as 3 and the other as 1 over 2. This is very similar to factoring, except we are guessing and checking directly for the roots. So we have x equals 3 or x equals 1 over 2 as our solutions. Square roots. Let us use an example. X squared minus 16 is equal to 0. This method is only used when b equals 0, that is, when there is no middle term. Rearrange the equation, and now we have x squared equals 16. Take the square root of both sides, and we have x equals plus or minus the square root of 16. We get x equals plus or minus 4. And that means the solutions are x equals 4 or x equals minus 4. Graphing. For the equation, x squared plus 11x plus 28 is equal to 0, we can plot it on a graph as follows. It cuts the x-axis at negative 7 and at negative 4. So the solutions are x equals -7 or x equals -4.